Hello everyone, my name is Yifei He. I'm a PhD student from the KTH Royal Institute of Technology in Stockholm. And today I'm gonna present our work on optimizing FDTD solvers for electronic magnetics, a compiler-guided approach with high-level tensor abstractions. Yeah, and this work is done together with my colleague Måns Andersen and my supervisor Stefano Markidis. Here is the outline of the talk. First, I will go through the background of the application, the FDTD method, and then I will talk about the methodology, about our domain-specific compiler framework, and later on is the performance evaluation and our conclusion. So first, about the mathematic background of the FDTD algorithm. FDTD, which is short for the Finite-Difference Time-Domain method, is one of the most commonly used method in the numerical simulation for to solve the Maxwell equations. And in the above, the two curl equations are from the Ampere and Faraday laws. And in the bottom, we can see it's the representation in the 3D tensor form using a Cartesian 3D geometry. And the E and H here represents for the electronic field and also the magnetic field component. And we can see that they have the equations on different directions, on 3 different directions for the 3D input. And on the left, we have a visualization of our application. So more about the FDTD algorithm. It actually requires high computational and memory access, because to have accurate electronic magnetic simulations, we need to have very high spatial and temporal resolution. So we need to have a large input size, and also we need to have many iterations to get the simulations. And also, it's basically a memory bound issue, because we need to update every point in each iteration, and the calculation is relatively not that complicated. And also, compared with the traditional FDTD implementations, which based on more like handwritten platform and application-specific code, they may have different kernels for different hardwares and different cases. So they are not portable across hardware and may perform well on some kernels and not on some unoptimized cases. So our work is like we have an end-to-end compiler for the FDTD program. We have an overview graph on here. We can see that the input is that we use the MLIR Python bindings to directly generate the FDTD algorithms in MLIR. And we have, for the operators we extended the linear algebra depth with the FDTD specific operations, which I will talk about later. And with the tensor representation, we apply some transformations like operator fusion and toweling. And after that, we managed to have the in-place bufferization. And here we have the different pipeline for vectorization, like for the fixed size vectorization for the x86 CPUs, and also the scalable vectorization for the ARM SVE extensions. And for the code generation, we use the LLVM. So here is the simplified Python version for our application. We can see on the left, here is the different functions to calculate first is how to update the H field components, to update the HX, HY, and HD, and then is the boundary conditions, followed by how to update the electronic field. So basically, for the main kernels on H and E, they have 3D input, and for the boundary condition, they have like 2D input. And on the right here is a naive Python implementation for one of the kernels. We can see that in this case, for how to calculate the HX, it will need the EY and EZ, but with different address. And also we apply this kind of calculation repeatedly on every point in the 3D input tensor. So basically, we can tensorize the computation because for the different points, they calculate independently. They don't have data dependence with each other, so we can make it into a tensor. And in the right bottom, here is a NumPy-based implementation because we kind of like express the computation in the matrix form. And also we can see that from the left, for the calculation of hx, hy, they have some kind of data reuse because they will read the same input buffer. So here we have the potential of using the operator fusion or loop fusion for better data reuse. And here is one of our implementation in the tensor abstraction. We extend the linear algebra dialect with our specific curl step operation. The curl step operation is used for both the H and the E fields, but with different tensors and different configurations. And also it's implemented using the linear algebra opDSL. Here the code is kind of like abridged for clarity and space. We can see that the code is in a single static assignment form. So unlike the Python code, which operates on buffers, here is like if we want to write to the tensor, we need to generate a different new tensor. And later on in the bufferization, I'll talk about later, we managed to eliminate the redundant tensors. And the main body operates on 3D tensors, and for the boundary condition, it's on 2D tensors. And here is a simplified code for the transform IR code we use in our optimization. We match the specific curl ops and then perform toweling and loop fusion and vectorization, which I will talk in detail later. First is the toweling. We can see that before toweling, we have some specific curl step, our custom ops, and after toweling, there will be a for-all parallel loop over a smaller ops on smaller data input, and the innermost dimension is set to the SIMD vectorization wide. For the vectorization, we have two pipelines, one for the x86 for the fixed vectorization. For the ARM platform, the fixed size vectorization also works, but it will only generate the Neon instructions instead of the SV instructions. But the SV instructions have better potential, so we tried a different pipeline and enable the scalable vectorization. On the right is the code example for in our code, like after the vectorization is in virtual vector code. Later on, when lowering down, it will lower to specific x86 or ARM code. And for the evaluation, we compared our FDTD application with the NumPy implementation, which is showed in the beginning, a NumPy matrix form implementation. And here we compared our performance on different data sizes from the input 64 to 1024. And here we compare the performance on both the single and double data. On the left, and all the performance is shown as speed up compared to a normalized NumPy implementation. On the left is the double implementation, double data precision implementation. On the right is the single data implementation. We can see generally the single data implementation would have like a 2 times speed up compared with the double implementation. And also our implementation have like up to 10 times speed up compared with the baseline. And here is like we tested on 2 platforms. On the Intel platforms, they would generate the AVX 512 code. And on the AMD, it would generate the AVX 256 code, but they both perform well. And also we tried it on the ARM A64FX code. Because our application would use lots of the memories, so here the ARM system we use doesn't have that much memory. So the largest input size was 512, because for the larger size, it will collapse. And for the ARM, there is one interesting thing we can see that is that for the for this single data precision, is not like 2 times more compared with the double precision, because we find that in the code that for the ARM code generation pipeline, although most of code is already vectorized and generates the SVE code, there's still a small portion of it that's like not vectorized. So for those part of scalar code, the double precision won't be like so for that part, it won't be like the single precision won't have 2 times more speed up. And in the right here is different optimization combinations we have to show the effect of different optimizations we applied. In the bottom is the code without any MLIR optimization I talked before, but with the some of the LLVM low-level optimizations. Above is the code after tiling, after vectorization, and after loop fusion. We can see that the most of the performance speed up comes from like after the vectorization. And for the loop fusion, it's like for small sizes, it doesn't really help much, but for large sizes, it would help better. Because that's also expected, because for small sizes, the data can be contained in cache. So yeah. And here is like we have a profiling for the performance counters for the applications of the NumPy implementation and our MLIR implementation on the Intel platform. And also some of the counters are normalized to the NumPy as 1x. We can see that in the bottom, like after tiling, we have like much less L1 cache loads, and much less L1 cache loads. And after the fusion, the L1 cache misses also drops significantly. And we also find that in the assembly hotspot of the NumPy implementation, they would generate some very expensive vector insert and structure operations. But in our implementation, there isn't such hotspot. We use the consecutive vector load and store instead. So in conclusion, is that we developed a high-level tensor abstraction for the FDTD kernels, and also we can apply some tiling and fusion on that abstractions. Also, we have a automated extraction of the hardware-specific parallelism. We enabled vectorization and some architecture-aware code generation for like Intel AMD and ARM CPUs. And in the end, we have some performance evaluation and an analysis for our implementation compared with the NumPy baseline, and have some speed up. Yeah, thanks everyone. That's my presentation.
So we have time for questions.
Thank you for the presentation. Yeah, I have a question. It's about do you try loop scaling? Loop scaling optimization for FTD algorithm. I mean, in polyhedral, the loop scaling is like from this to this. Yeah, it's also a good optimization method for FDTD computation. Because in the benchmark, the FDTD and ADI and Jacobi and HIT, it named this has a common name. It named stencil computation. Stencil, yeah.
Yeah, stencil, yeah.
So I mean, this method is suitable for other stencil computation. And another I mean, if it's suitable, then in polyhedral module, you can abstract your method into a custom module. Then polyhedral can out-schedule this method for any stencil computation. Yeah, thank you.
Yeah, thanks for your question. Right now, we don't have the optimization, like you said, the loop scaling, and also we don't have the polyhedral model in our scheduling. But the loop scaling, for sure, it looks very promising. So later on, when we optimizing it further, we might, like what you said, to apply some other stencil code, some stencil patterns, optimization patterns. Yeah, but right now we don't have those. Yeah.
Okay, thank you. Thank you.
Hello, thanks for the talk. So my understanding, I'm not so familiar with this problem, but my understanding from the talk was that this is also very memory bound as well as time bound. Did you evaluate the memory usage of your method compared to the NumPy methods, or is it not change, or does that make sense? I don't know.
Memory usage, you mean the memory usage of the main memory?
As in, so whichever one is like the constrained one. I don't know. My understanding is that this problem uses a lot of memory.
Yeah.
Does your method lower the like max memory usage you need at all, or is it constant? Is it more?
Yeah. Here is one of the profiling results. I would say that for the total memory usage, it would be the same because the algorithm they need to traverse the whole input data. But here's like by applying something like tiling and fusion, we can improve the data reuse, like utilizing the locality in the data access. So here we have better like L1 cache or last level cache reference. But the total memory usage, I would say it would be the same. Yeah.
Okay. Thank you.
Yeah.
Are you familiar? There has been an effort, I think, last year on getting a stencil dialect for MLIR, so that you can express these operations in like an MLIR dialect that has low rings for GPU and CPU and even like open MPI support. Are you familiar with that work?
I'm not familiar, but I heard of that work. Yeah, there are some stencil application. But here it's like our work is more like specific to this like overall problem. And like you said, for the stencil optimization, actually there are already some of the like MLIR implementations or some implementation not based on MLIR, but still very fancy. Here it's like our work is like more like focused on the overall problem we met. And for sure, later on, we can dive deeply into it and apply some of the optimizations they already there for the stencil code. Yeah, and also we have a GPU implementation, but right now it's not like fully optimized, so I didn't show the result here. Yeah.
Okay, thank you.
Yeah.
So have you think about try on RISC-V vector extension, some of the RISC-V platforms?
Yeah, I think RISC-V is like a very popular and promising hardware. For sure, I would like to try, but right now, as our project motivation, we don't have that needs. But for sure, it's very interesting. Not just this application, but maybe some other application. RISC-V is for sure a must try. Yeah.
Okay, thank you. Thank you, speaker. Thank you.